Hi everybody, welcome to our next topic in grade 12 physics. And today we're going to be building on our topics in electrical energy and electric fields. And what we're looking at today is electric potential energy and electric potential. And I'm going to warn you that the terms here get a little similar and can be easily confused. So we want to make sure that we're very precise and very specific in our language here. And so we'll certainly cross the bridge when we come to it, but just something to keep in the back of your mind that some of these terms will be very, very similar in their naming, but certainly have different meanings. All right, so let's start with something you should know, the electric field. And remember, the electric field is given by this epsilon vector. And so it's actually a measure of how strong a force would be at that location if there were a test charge there. And of course, we decided on a positive test charge. And so for a point charge, we end up with this expression here. And again, so that's our expression for electric field around a point charge. But in general, the electric field is written just as the force experienced by some charge divided by that charge. So you're removing the charge from that to talk about really the effect of only that one certain object or charge that's there. All right, so on to the new sort of ideas. So the first one we're going to talk about is electric potential energy. So electric potential energy, again, we have sort of analog that you're very comfortable with, this idea of electric potential, gravitational potential energy. And so what electric potential energy is just the energy stored when two charges are close together or separated by some distance. So for instance, if we have two objects here, Q1 and Q2, being there, they're exerting a force on each other, and they no matter where you're going to place them, they're going to exert a force on each other, and so there is some energy stored there. So I'm not going to go through that whole method again for deriving the expression. It's very similar to gravitational energy, but it turns out to be this. So the energy stored between two points two charges is given by just this expression here. And the electrical energy is going to be given in joules, just like you'd expect. But you may be saying, well, wait a second, Mr. Young, this looks a little different because if you remember that for gravity there was actually a negative sign in there. And it's going to be different again because electrical energy or electrical forces can be positive or negative, attractive or repulsive. So how the heck is that supposed to fit in? Well, luckily the equation will take care of itself. And it has to do with the signs here. So if Q1 is greater than 0, or that means it's positive, and Q2 is greater than 0 or positive, what that means is then we're going to have our electric energy is greater than 0. You can see that just from this expression up here. And if electrical energy is greater than 0, what that means is they have more potential energy stored. So the closer you bring them together, the more energy, the positive energy that is stored, it takes work to bring them there. It takes force to bring those closer together. And so because those charges are repelled from each other. We can actually repeat that idea if we say the second charge is negative and the first charge is negative. We have the exact same scenario. We have the fact the energy stored is greater than 0, which means again that the charges that are closer together have more energy stored. It takes work to bring them closer together. If we take a look at the opposite examples, so one positive, one negative, so this case here or this case here, we've actually got the energy as negative. And this is very similar to the gravitational potential energy. Again, if I have two objects or two charges that are close to each other, they'll be attracted to each other, and objects that are closer have less potential energy stored. But in either one or any of these four cases, the same reference point exists. Our same reference point will be infinity. That's we're going to say that these charges that are infinitely far away have no potential energy stored between them. Okay, so let's take a look at what does this look like over sort of distances. So we're going to look at how the energy changes versus separation. And notice again there are two curves here. Why are there two curves? Because we have to worry about signs. When the charges have the same sign, or when what that means is the force is repulsive here, we're going to be in this top section. So we'll be up in this section up here in the top. And when the charges are attractive, where they're the opposite sign, we're going to be in the lower half. And again, notice both cases, as r goes to infinity, the stored energy here goes to 0. But how it gets there is different. So if I actually have an object here, say right here, and I let it go, what's going to happen? Well, it's going to go flying away the stored potential energy will be released. It will turn into kinetic energy, and this thing's separation will increase. But if I have an object like this and I let it go, what's actually happens is it's going to be coming down this way because it's going to be coming close together, attracted together. And something that's kind of neat, you can actually generalize this sort of statement, that whenever we graph an energy versus distance graph like this, objects will always tend to go down towards the bottom of the potential if left to their own devices. Nature will find a way to bring things down. And so objects will always try to have the lowest sort of energy state. And this is, again, one of those cool fundamental ideas of the universe, and we'll talk a little bit more about it a little bit later on. All right, so there's enough out of that. So as I said, there's a couple similar terms today, and so we already talked about electric potential energy, and now we're going to talk about something called electric potential. A very similar idea, or at least a very similar term, but it is slightly different, so we have to make sure we're careful here. But just like we talked about gravitational field, by removing the sort of test mass, when we were talking about the gravitational force, we're going to do the same sort of thing with electric potential energy. So what that means is we're going to kind of remove that test object. We're not going to have to talk about another object. So we're going to just pretend that it's like a unit charge, and we're going to define this electric potential as the energy sort of stored per charge. So the electric potential is the electric potential energy stored per unit test charge. So how much energy is stored for every coulomb that is there. And we're actually going to use the electric potential energy in a unit you've probably heard of before, volts. And so, sorry, where am I going here? Oh, so for if we're having a point charge, not point form, here's the problem. If we have a point charge, the electric potential in the region around it simplifies to this, which again is just our electrical potential energy with the one charge canceled out. So what we can say is that Q1 has an electric potential of V in the space around it, and it only depends on R, its separation from it. And so, for instance, to kind of bring this home, what we're really talking about here is this idea here, that if I have a location in space that has, let's say, an electric potential of, let's say right here has an electric potential of 20 volts, what that means is if I were to have a 1 coulomb, positive 1 coulomb test charge initially at infinity, and I want to bring it all the way here, I'd have to do 20 joules of work, or how much energy I'd have to store in this system in order to do that. So that's sort of the idea of what electric potential means. And just to confuse you a little more, there's one more term here, electric potential difference. So electric potential uses infinity as its, or infinitely far away as its reference point. But often, especially when we deal with electronics, infinity is something that we really don't want to have to deal with. So we're going to deal with often something called electric potential difference. And in grade 9, when you guys did electric circuits, or in grade 11 when you did them as well, you talked about voltage. What you were really talking about is electric potential difference. So when you said there was a 9-volt battery or something, you were talking about electric potential difference. And all electric potential difference is the difference in electric potential between 2 points, kind of what the name sounds like. So for instance, if I have an electric potential difference, so I'm just going to write it like this right now so I can be lazy, is let's say 6 volts. That means the difference in electric potential from this point, let's call it A, and this point B, is 6 volts. So it takes 6 joules more to move a coulomb from one to the other. So that's what that's talking about there. Now the nice thing though is that it's actually path independent. And what I mean by that is that if I want to take, let's say, this charge A, or charge Q from A to B, it doesn't make a lick of difference how I get there. If I go and follow this blue path, the electric potential energy, or the work I had to do, is the same as if I took this red path, or if I took this crazy, fun, spiral black path. All those paths would take the same amount of total work or total energy transfer to do that. And that's going to help us a little bit later on, which is kind of cool. All right, so as I said, we've got some terms that are very similar. And so let's try and clarify some of them, make sure no one's going to be confused here. So I've got 5 terms here that I think are pretty similar. So what I want you to do for me here is pause the video, and I want you to think about what each of these terms mean and what makes them different and similar about each other. So again, pause the video here, think about those. When you're ready, restart the video, and we'll look at what I have for that. All right, so again, I hope you've done that and you have an idea here. So the first one here, the first sort of idea we looked at was the electric force. And the electric force, that one's not terribly difficult, hopefully. That's just the force acting between 2 charged objects. So if I have 2 objects that have a charge, there'll be a force between them, and that force is called the electric force. The electric field is all about removing one of those objects. So it's saying, let's just have one of those objects, and what would it do to an object that was around it? So the region in which a force would be exerted on a charged object if it were to exist. And we could talk about kind of quantifying that with this vector epsilon, an electric force, for using the symbol Fe. All right, electric potential energy. That's the energy stored to the position of 2 or more charged objects. Another way to say it is the energy required to bring 2 charges together from infinitely far apart. So I have 2 objects way, way far apart, like here and here, and I want to ram them, so this one's here. It's a measure of how much energy I have to do that. And the symbol used for this one is EE. All right, electric potential. That is the electric potential energy per unit positive charge at a region in space. So it's like taking the potential energy, but again, removing that test object and saying, if that were the only one there, how much work would it take to bring a 1 coulomb charge in there? And the symbol you get for that one is V. And the last one that I said is kind of similar here, electric potential difference, and that's just the difference in potential, electric potential between 2 points in space. And so the symbol you give that one often is like VAB, or we can say like delta V. So electric potential difference, so change in between A and B, or just delta V. All right, so now that we've hopefully got these terms straight, we've got these ideas straight in our mind, we've got 3 new ones to look at. We learned today. Let's do some examples. First one, what is the electric potential energy stored between 2 point charges separated by a distance of 0.10 meters? If the charges are, and here are 3 sort of options. So all of these are point charges, and so for all of them we've got, say, object 1, object 2, and the nice thing is they all have the exact same radius, looks like a smiley face, of 0.10 meters. All right, and we want to know again for the electric potential energy. So what is that one? Again, that's the energy stored in the system, how much work it took to bring these 2 charges together, and the symbol is given by EE. And it's just given by K, Q, or I guess Q1, Q2, divided by R. And so now it's just a matter of shoving these in, but watch carefully for the negative sign. And so for A, when I did it, I've got an answer of negative 0.52 joules. So again, please do that. Make sure you get the same answer I did, that I didn't make a mistake, or that you didn't. And what does that represent? That represents that to take those 2 charges from infinitely far away, I'm actually releasing 0.52 joules of potential energy. And this again makes sense because these 2 charges, a negative and a positive, would be attracted to each other. And so they'd actually then be having less potential energy now because they're closer together. All right, so repeat for B. Again, same equation we've got here, but different numbers. So I'm getting 9.9 joules. It's a positive number. And again, that makes sense because they're both 10.5 positive microcoulombs. What that again means is that these 2 objects are repelling each other. So I had to do positive work to bring these 2 objects together. And C, I'm getting the exact same number, which at first glance sounds strange, because this is negative 10.5 microcoulombs, and this is positive 10.5 microcoulombs, and the exact same energy stored. But remember 2 things to keep in mind. One, our choices of positive and negative were completely arbitrary. The universe doesn't care which one we picked, and so it's really, it's actually nice that it turned out the same. And the other thing to keep in mind is that both of these are causing a repulsion, and so that's well, it should be the same because they're both repelling in the same sort of magnitude. All right, next one. What is the electric potential a distance of 0.45 meters away from a negative 1.25 microcoulomb point charge. All right, so we've got a point charge here. Its charge is negative 1.25 microcoulombs. And I'm at some distance away. Let's say I'm over here. I'm going to call it with an X. And that distance is 0.45 meters. And I want to know the electric potential. So again, probably the most important thing to ask ourselves here is, what the heck is electric potential? And what is it we're trying to find? So electric potential, again, that's our V. That's the energy stored per charge. So electric energy per charge. So if I were to put a 1 coulomb charge right here, how much energy would it store? How much work would I have to do? And so since this is a point charge, we can just write this as K. Let's call it, I don't know, capital Q. Actually, no, I already called it. Maybe I should be careful with my terms here. Let's call this, sorry, just to avoid confusion here, let's call this capital Q. So that's capital Q over R. And the reason I'm doing that is, again, because little q we're normally using for our test charge. Sorry about that. And again, now it's just a matter of shoving these numbers in, and I'm getting a voltage of negative 25 kilovolts, or negative 25,000 volts. So again, what does that mean? It means that if I were to take a positive test charge of 1 coulomb all the way from infinity, so it's 0.45 meters away, it would release 25,000 joules of energy. Or another way to say it, if I have a 1 coulomb charge right here and I wanted to rip it away, take it all the way away from that microcoulomb point charge, I'd have to put in 25,000 joules worth of work. All right, so one last example for you guys here. What is the electric potential difference between these 2 points, A and B shown? And what I mean by that is, if I want to take an object from A to B, what is the electric potential difference? So what is that again I'm really asking for? I'm asking for VBA. What is the difference in electric potential from B to A? So all it is the difference in electric potential, or the voltage between B and A. So that's just KQ, and again I'm using, I guess, it should be clear, this is Q over RB minus KQ over RA. Do a little common factoring here to make my life easier. KQ 1 over RB minus 1 over RA. And again, I'm going to leave the actual calculation to you there, or at least to verify with me, but I'm getting 7.7 kilovolts. And again, let's pause and ask ourselves, what the heck did we just discover? What did we just find out? We found out that if I want to take a positive 1 coulomb test charge from here to here along any path, it would take 7,700 joules of work to do so. Okay, so again, I hope that makes sense and everybody's good with that. So again, just like last time, there should be 3 quick questions at the bottom of this video. So try those for me, and we'll talk about any issues you have in class tomorrow. Have a great night, everybody.